In this lecture set, we will be dealing with constraint optimization. In contrast to the previous lecture set where we dealt with unconstrained optimization, here the optimization problem has constraints. And in contrast to the linear programming problem that we had earlier, uh, the objective function or the constraints or the constraints may not necessarily be linear. And so how do you find optimizers in this case? This is the subject of the next set of slides. So in the previous problem of unconstrained optimization, we see here that we have a domain which is a convex set. Okay, so this is the domain over here. And then imagine a dome. Okay, so this must be a three-dimensional figure. Okay, just imagine a dome like this one. Okay, and then this is the convex set, which is the domain. And then our task was to find the points x star, y star, okay, x star, y star, where this function is maximized. Okay, so you could imagine a point here. This one is parallel to the x-axis. Okay, so this is an x star and a y star over here, such that we find these points, these optimizers that would give the highest value of the function. Now notice that we didn't put any constraints on the domain. Okay? And in the next set of slides, we will put some constraints on the domain and see where the maximum lies. So now in contrast with the previous slide, here we will maximize the function subject to a constraint. Okay? And the constraint says that I will find points x and y such that ax plus by equals to c. And this is the line where every point here in this line, okay, every point in this line is such that ax plus by, these are combinations of x and y such that ax plus by equals to a number or a constancy. Okay? So you're restricting basically the domain to this slice of the line. Great. Now in this slice, given this constraint, you see now that the maximum, in this case, this maximum can be necessarily different from the unconstrained maximum over here. So here we have x star, y star, right? So x star and y star maximizes this larger dome, so to speak. But now we have this constraint over here, and x star, y star may not be feasible, okay, or may not satisfy the constraint. So therefore, there's another combination, probably different in this case, x star star, y star star, okay, such that this is just heuristic, so don't fault me if I did not draw this accurately. But the point is that there are a new set of optimizers where the function constrained here in this line will attain, where the function will attain its maximum. Okay, so in this case, this is fx star star, y star star. Okay, so the point is, if you introduce constraints, the set of optimizers may be different compared to the case where you have an unconstrained maximum. Let's go to the first case where we deal with problems, with optimization problems with one equality constraint. Okay, so this is the operative word. We only have one constraint, and it holds with equality. It has an equal sign. Okay, and then we have two variables in our function. So this is the problem. We want to maximize or minimize a function. Now this function is a function of two variables, x and y. Okay, we want to maximize or minimize that function subject to a constraint. Okay, the constraint is a function g, so it's not necessarily linear. Okay, it can be any functional form. So this constraint is also a function of x and y, right? And this b is a number, but the important thing is this holds with equality. Okay, so the constraints holds with equality. Later in the slides, we'll deal with how to find the optimizers when constraints have inequalities in them. But in this case, our main concern is a problem where we have a function of two variables and the constraint is holding with equality. Okay, so we have an equality constraint. We have an equality sign, an equal sign in the constraint. So to solve this problem, we discuss the Lagrange multiplier method. So we have this problem. So suppose we have the problem where you want to maximize or minimize a function of two variables x and y. And this function, this maximization or minimization problem is subject to a constraint where the constraint holds with equality. Okay? Now the constraint can be a function of x and y, and it's not necessarily linear, it's a function g. Okay? So now we define what's called the Lagrangian of this problem. Okay? So the Lagrangian of the problem is defined this way. So the Lagrangian is a function of three arguments. You have lambda, you have x, and you have y. Okay, so the Lagrangian is defined this way. It's the objective function f x of y, great, plus lambda, and this is the constraint b minus g of x and y. Okay, so you have b here, and you have minus g here, and then you multiply that by a parameter lambda. This parameter, this scalar lambda, is called the Lagrange multiplier. Okay? So here, when you have a positive lambda, it's b minus g xy. Okay? But the Lagrangian can also be written like this one. So you have the objective function f of xy minus lambda, contrast that to the plus lambda here. If you have a minus lambda here, then g should be here. So it's gxy minus b. Basically, you just flip the arguments here above. So you can either write it this way or write it this way. But basically, this is the Lagrangian of the problem. Now, suppose you have this maximization problem. You want to maximize the function f of xy subject to a constraint, g of xy equals to b. Now notice that this constraint over here are just combinations of x and y that will, once plugged into the function, will equal to a number b. Okay, so in other words, this is a level curve. Okay, so for example, you have a function like this, okay, such that all points x and y, all combinations of x and y, so this is x, this is y, this one is x1, y1, this is x2, y2, okay? Now all these points, all these combinations of x and y, once plugged into the function, so gx1, y1 is equal to a number b, okay? And gx2, y2 is equal to the number b. Great. So again, these are combinations of x and y. When plugged into the function, it spits out b, a number b. So this is a level curve. So the feasible points are those that lie on this curve, okay, on this constraint. This level curve, therefore, is called the constraint curve. Okay? Now, like I said, we have the constraint curve, and it's denoted by this dark blue line. Okay? This is the constraint curve. Again, all points here, x1, y1, if we have x1, y1 here, and then x2, y2, all points in this curve, once entered into the function g, is spitting out b. Okay, so If you enter x1, y1 into the function g, it will spit out b. If you enter x2, y2 in the function g, it will spit out b. Okay, so that's the constraint curve over here. So as discussed, this is a level curve of the function g. Now, notice that the objective function is also a level curve. Okay, and this is depicted by this red. Is this red or yeah? This red lines over here. Now, as discussed, this level curve, for instance, this line over here gives the combinations of x and y such that it spits out a number C1. Okay, it's any number. Now, this higher level curve over here are combinations of x and y such that it spits out C2. Now, C2 here is bigger than C1. Okay, so the higher the level curve or the farther away from the origin, it gives a higher value of the function. So again, all the points here, say x3, y3, and x4, y4, okay? So if you plug in f of x3, y3 here, it will give you C1. If you plug in x4, y4 in the function f, it will give you C1. Okay? So these are combinations of x and y that when plugged into the function f, it will spit out C1. So in the same manner, if you have combinations here, x5, y5, and x6, y6 over here, now f of x6, y6, or x5, y5 first, okay, will spit out C2. Then f of x6, y6 will also spit out C2. Okay, great. So that's the definition of the level curve. Now, as I've said, the further you are from the origin, okay, the further you are from the origin of the level curve, the further it is away from the origin, then the higher the value of the function. So in this case, C2 is bigger than C1. Okay, great, great. Now notice, if it is the case that level curves of f of the objective functions are increasing when you move away from the origin, then basically the maximization problem is to find the highest level curve that just satisfies the constraint, okay? So it is to find the level curve that just touches this constraint defined by g of xy equals to b, okay? So here, you have this constraint over here. Now you move from this level curve, okay, from this level curve, it gives you C1 to this level curve, it gives you C2. Okay, what I mean by C1 is f of xy is equal to C1, and then f of xy is equal to C2. You notice that C2 is bigger than C1 in this case. So you push out, the maximization problem is basically just pushing out that level curve until it satisfies the constraint. Okay? Now notice that this C2 satisfies the constraint because you have bundles that are in the line. Okay? But we can find a higher level curve for f where it still satisfies the constraint and it pushes out this level curve, which gives you higher value of the function. So in this case, this thick red level curve is higher than this thin level curve over here, but at x star y star, which is this one, this bundle x star y star is on the constraint, and so therefore it's feasible, okay? And the thick red indifference curve here gives you the highest value of the function. Okay? So what do you notice? You notice that since they touch, this level curve is tangent to the constraint curve, meaning that they share the same slope. Okay, so let's just change this color. So you notice that the slope of the uh, tangent curve, the slope of this curve is the slope of the budget line at point x star y star, and the slope of the red level curve at x star y star. So at x star y star, okay, at x star y star, the slopes of this constraint curve, okay, and the level curve are equal. Okay? So since we have the level curve defined by f, okay, we know that from the implicit function theorem. Okay, so if you want to review the implicit function theorem, just go to the lecture set on differentiation, and just review that part. But due to the implicit function theorem, we can find the slope of that level curve f, okay, this level curve. We can find that slope, okay, this slope, so this is x, this is y. We can find the slope via this expression negative f of x divided by f of y, or negative fx divided by fy, which is the partial derivative of f with respect to x, and this one is the partial derivative of f with respect to y. Okay, this is due to the implicit function theorem. Okay, and similarly, that constraint curve that we have, okay, so this is f of xy equals to c. This is the level curve. This is also a level curve, g of xy equals to b. So to get the slope at the point, okay, to get the slope at the point, at a certain point xy, via the implicit function theorem, this can be expressed as gx negative of gx divided by gy, where gx is the partial derivative of the function g with respect to x, and gy is a partial derivative of the function g equals to y, with respect to y. Okay, good. So again, these two are offshoots of the implicit function theorem. Now, notice that, as we said a while ago, when we had that figure at the optimal point, okay, the slopes of f and g, this level curve f of xy equals to c, and g of xy equals to b are equal. Okay, so this is x star, this is y star. Okay, so at x star, y star, the slopes of the level curve defined by f and the level curve defined by g are equal. So therefore, at x star, y star, this slope is equal to this slope, or this expression over here. Okay, so this is true at x star, y star. Okay, at the point x star, y star. Okay, so from the previous slide, we have that negative f of x star, y star, over fy, x star, y star is equal to negative gx, x star, y star, okay, over gy, x star, y star. Okay. And so therefore, what you can do is to flip things around. So if you move this to this side and you move this to this side, you have f of x, x star, y star, f of y, x star, y star, oops, is equal to gx, x star, y star, over gy, x star, y star. Great. And then if you move things around, we have that, okay, so if you move gx here, okay, and you move gy here, okay, so you can express this as, or fy, or the other way around, sorry about that, So if you have that, move f gx to this and move fy to this numerator, then we have the expression f x x star y star over gx x star y star equals to fy x star y star over gy x star y star. Okay? Great, and that is this expression over here. Okay, great. Now notice that f and g are functions, okay? And if you plug in certain values like x star and y star are numbers, okay? Certain numbers. So if you plug in that, it will give you a number, okay? So define that number by lambda star, okay? So lambda star is just a number where you plug in x star and y star to the functions fx and gx, okay? So this is equal to lambda star, okay, a particular value, and this is also equal to lambda star, particular value, okay? Because these expressions are equal. They're both equal to a certain value or a certain number lambda star. Great. Okay, now let's take this first. Lambda star is equal to f of x, x star y star over gx, x star y star. Okay, okay. So if you move things around, we have that. Okay, so you move gx here to lambda, and then you move all that to here, to this side, then you have f of x, x star y star, okay, minus lambda star gx x star y star, okay, is equal to 0. So this is this expression over here. Okay, in the same manner, take lambda star is equal to f of y x star y star and g of y x star y star. If you move things around, okay, move gy here and multiply it with lambda, and then move all that expression to here. So you have fy x star y star minus lambda star gy x star y star, okay, equals to 0, which is this expression over here. Okay, great. So that's how you get this and this. Now, you notice that x star y star, okay, if we have this point x star y star over here, we have the points x star y star over here, and this is the level curve fxy equals to c, and this is the level curve gxy equals to b. Okay, so at this point, at point x star y star, it's on the line, so therefore it satisfies the constraint. Okay, so if you plug in x star y star to g, it should equal b. Great, because it's on the curve. It's on the curve. So therefore, moving things around, if you move g here, you have b minus g x star y star. Great, which is equal to 0. Okay, so that's how you get this three conditions over here. So the three conditions that we had in the previous slide characterizes this theorem, which gives the necessary condition for optimality. So the theorem goes like this. So suppose you have a problem which you want to maximize or minimize function f, which is a function of two variables x and y, subject to a constraint g, which is also a function of x and y, which is equal to b. So holds with equality, and assume that f, both f and g, the functions f here and the function g here, have continuous partial derivatives. Now let x star y star be optimizers such that g of x and g of y is not equal, are both not equal to 0. Okay? Then there exists a scalar lambda star such that x star, y star, and lambda star satisfies the three equations that we had earlier, namely b minus gxy equals to 0, fx plus lambda gx equals to 0, and fy plus lambda gy equals to 0. Okay, so this gives a necessary condition for optimality. Now, those three conditions of the previous slide can also be cast in terms of the Lagrangian. Okay, so recall that the Lagrangian function, which is a function of lambda x and y, is just simply constructed by having here the objective function f of xy plus lambda times b minus g xy, which is found in the constraint. Okay, now notice that if you take the derivative of L, the partial derivative of L with respect to lambda, now lambda only appears here, so the partial derivative of L with respect to lambda is just this term, which is b minus g xy. And then you equate that to 0. Okay? And then if you take the partial derivative of L, the Lagrangian function, with respect to x, so x appears here. Okay? So therefore, you get the partial derivative of f with respect to x, which is fx. Okay? And x appears here. So you have lambda, which is a scalar. Okay? We have a negative sign here. So because the negative sign can be, lambda as an expression can be negative or positive. So by convention, let's just call it positive lambda. Okay? So lambda can be positive or negative. So therefore, we can just have positive lambda. Okay? And so we have lambda times the partial derivative of g with respect to x. Okay? And then if you get the partial derivative of the Lagrangian with respect to y, we have y here. So we have the partial derivative of f with respect to y, which is fy. Okay? And then the partial derivative of g with respect to y, gy, times lambda. This is this term. Now, you may be confused because there's a negative here. How come the negative doesn't appear here? Well, lambda can be any number, so we'll just put a plus sign over here. If it's negative, then this becomes negative. Okay, if it's positive, then it becomes positive. Okay, so basically these are the three conditions which are similar to the conditions in the previous slide. Okay, so these conditions are also characterized by the gradient of the Lagrangian function and equating it to 0. We've discussed the necessary conditions for optimality. Now, how would you know that the x star, y star that you get, or those optimizers, are minimizers or maximizers? Okay, so we have the sufficient condition for optimality, which is stated in this next theorem. This theorem says that given an optimization problem, whether you maximize or minimize a function f subject to a constraint g equals to b, g of xy equals to b, and then f and g have continuous second order partial derivatives. Okay, this is important. So suppose we have lambda star, x star, and y star to be stationary points of the Lagrangian function, Lagrangian L, okay, where gx is not equal to 0 and gy is not equal to 0 when you plug in x star and y star. And Let H be the Hessian matrix of L. So what's the Hessian matrix here in this case? So you have L equals to f of xy, okay, plus lambda b minus g of xy. Okay? So that's your Lagrangian function L. What is the Hessian matrix of L? Well, the Hessian matrix of L is defined by second order partial derivative. So in this case is, um, let's make this clearer. Uh, H, the Hessian matrix H is a function of lambda x and y. Okay? So therefore, the Hessian matrix is defined by the second order derivatives. And so we have here L, okay, with respect to lambda, lambda, okay, and then the derivative of L, lambda x, okay, and then L, lambda y, you have lambda, L, uh, x lambda, then you have L x x and L x y here. And then finally we have L y lambda, L y x, and then L y y. Okay, so these are second order partial derivatives of the Lagrangian function. Okay, so this is the Hessian. Okay, so what are the conditions? What if the determinant of the Hessian matrix is negative? So get the determinant of this Hessian matrix and evaluate it at lambda star, x star, and y star. Okay, plug in lambda star, x star, and y star, and once you plug it in, it's negative. Then your stationary points x star, y star are strict local minimizers of f. Okay, so that point x star, y star is a strict local minimizer of f. When the determinant of the Hessian matrix is negative, when you plug in lambda star, x star, and y star. This is important. On the other hand, if the determinant of the Hessian matrix, once you plug in lambda star, x star, and y star is positive, then the stationary point x star, y star is a strict local maximizer of f. Okay? So in order for you to determine whether the stationary points is a minimizer or a maximizer, then you have to look at the determinant of the Hessian matrix evaluated at lambda star, x star, y star. Now, the previous discussion may seem abstract, and we'll go now to an example to illustrate the concepts that we have just discussed. Okay, suppose you have a problem where you want to minimize the function x squared plus y squared. So this is your f of xy. Okay, this is x squared y squared, x squared plus y squared. Great. And you have the constraint x plus y equals 2, so it's of the form gxy equals to b. In this case, your g of xy is equal to x plus y, and your b is equal to the number 2. Great. So you want to minimize that. So here I will provide sort of a recipe, okay, on how to solve such problems where you have two variables for the function x, y, and where the constraint holds with equality. So the first step is to set up the Lagrangian. Okay, so what's the Lagrangian? As discussed, the Lagrangian is just f xy plus lambda b minus g xy. Great. Okay. And so therefore, this f of xy, the Lagrangian is composed of f of xy, which is this one, okay, and then plus lambda b, which is 2, okay, this is your b, minus gxy, okay. So your gxy is x plus y, the negative of that is negative x minus y. So that's a Lagrangian. Okay. Now the second step is to differentiate this Lagrangian L with respect to the to lambda x and y. So getting the first order partial derivative of the Lagrangian with respect to lambda. Okay, so lambda appears here. So lambda and the derivative of the Lagrangian with respect to lambda is just this expression, 2 minus x minus y. Great. Now the first order derivative, partial derivative of the Lagrangian with respect to x appears here. Okay, so you have 2x, okay, and then x appears here, so you have negative lambda. Okay, great. Now finally, the first order partial derivative of the Lagrangian L with respect to y appears here. So we have the derivative of that is 2y, and then y appears here. So it's negative 1 times lambda, which is negative lambda. Okay? And so the next step is just from the fact of the first order necessary conditions, the condition in that first order necessary condition where we equate the gradient of L, or the first order partial derivatives, equal to 0. So this is, oops, this here is uh, the first partial derivative of the Lagrangian with respect to lambda. You equate that to 0. Here it's the first order partial derivative of the Lagrangian with respect to x. You equate that to 0, and this is the first order partial derivative of the Lagrangian with respect to y. Okay, so we derived that in the previous slide. Okay, so when you set that equal to 0 and you solve for lambda star, x star, and y star to satisfy these three equations, then you find the stationary points of the Lagrangian. Okay, so in this case, we know that lambda equals to 2x, okay, and lambda equals to 2y. So if you equate this, then 2x equals to 2y, x equals to y. Okay, so using this fact in the first equation, we have 2 minus x, since x equals to y or y equals to x, then you have another x here equals to 0. So 2 minus 2x equals to 0. This means that 2x equals to 2. So x star is equal to 1. Okay? Since x equals to y, then the y star here is also equal to 1. Okay, because of this condition. Now, since lambda here is equal to 2x, so lambda star is equal to 2 times 1 is equal to 2. So therefore, you have these stationary points of the Lagrangian L. Now that you found the stationary points, you want to know whether those are local minimizers. Okay, so strict local minimizers. So in the second order in the sufficient condition, we should look at the second order partial derivatives, or the Hessian. So this is the next step. What we'll do is find the Hessian matrix of L. Again, the Hessian matrix is just the matrix of second order partial derivatives. So we have the first order partial derivatives that we have just derived a couple of slides ago. Now L lambda lambda over here is the partial derivative of L lambda with respect to lambda. Since lambda doesn't appear here, okay, it's equal to 0. L lambda x over here is the partial derivative of the first equation L lambda with respect to x. And x appears here, so the derivative of that is negative 1. Right? And L lambda y is the partial derivative of L lambda with respect to y. Y appears here, so it's equal to negative 1. Great. And Lx lambda is the partial derivative of this function Lx with respect to lambda. Lambda appears here, so there's a negative 1 here. Lambda xx is the partial derivative of Lx with respect to x, so x appears here. So therefore, this derivative is equal to 2. And Lxy is the derivative of Lx with respect to y. Y doesn't appear here. Okay, so therefore, Lxy equals to 0. And finally, Ly lambda, okay, is the derivative of Ly, this equation, with respect to lambda. Lambda appears here, so it's -1. Lyx is the derivative of Ly with respect to x. X doesn't appear anywhere, so it's equal to 0. And then Lyy is the derivative of Ly with respect to y, which is equal to 2 because of this expression over here. Great. So therefore, the Hessian matrix of this Lagrangian, which is a function of lambda xy, okay? In this case, there are no expressions involving lambda x and y, but this is 0, -1, -1, -1, 2, 0, -1, 0, 2. Now the next step is to, well, first you have to evaluate the Hessian at lambda star, x star, y star. Okay? But since there are no lambda x and y terms in this Hessian matrix, so therefore the Hessian evaluated at lambda x star, y star is this matrix itself. Okay? We don't have to substitute anything. Great. So the next step, step 5, so we want to determine whether it's a strict local minimizer. What's the theorem? What does the theorem say? You have to look at the determinant of this Hessian matrix. Well, you can check it by yourself, but the determinant of this Hessian matrix is equal to -4. Okay. So therefore, that determinant is less than 0. It's negative. In the next step, in step 6, we'll use that fact to determine the type of stationary points. So therefore, that stationary point x star equals to 1 and y star equals to 1 is a local minimizer of f because the determinant of the Hessian matrix is negative. Okay, that's what the theorem says. So now we stopped at the condition to determine whether the stationary point is a strict local maximizer or a strict local minimizer. Okay, so the second order sufficient condition gives the formula for that, or the conditions for determining whether it's a local minimizer or local maximizer, those stationary points. But we want to go a bit further. Okay, we want to know whether those local minimizers are global maximizers. This should be minimizer. Okay, whether the local minimizer is a global minimizer. Okay, so in order for you to do that, you want to determine the concavity or convexity of the objective function. In this case, our objective function is x squared plus y squared. Okay, so how do you determine concavity or convexity? Well, you need to look at the Hessian of the objective function. Okay, so this Hessian h of xy is equal to fxx fxy, okay, fyx fyy. Great. So fxx will fx first is just the derivative, first order partial derivative of f with respect to x, which is equal to 2x. And the f of y is the first order partial derivative of f with respect to y. In this case, it's equal to 2y. So fxx is the derivative of fx with respect to x. So it's 2. Okay. Fxy is the derivative of fx with respect to y. Y doesn't appear here, so it's equal to 0. Fyx is the derivative of fy with respect to x. X doesn't appear in this case, so it's equal to 0. And then fyy is the derivative of fy with respect to y, which is equal to 2. Okay, so this is the Hessian of the objective function. Okay, so don't be confused. This is the Hessian of the objective function. And the reason we're getting this is to determine the concavity or convexity of the objective function. This is not the same as getting the Hessian of the Lagrangian that we had a while ago. So the Hessian of the Lagrangian is used to determine whether the stationary points are strict local maximizers or minimizers. Okay, so don't be confused. Here we're just determining the convexity or concavity of the objective function. That's why we get the Hessian of the objective function, f. Now this Hessian here is positive definite because the leading principal minors are all positive. So therefore, by the theorem that we had a while ago, if your Hessian is positive definite, then the function is a strictly convex function. Okay? So based on another theorem that we had previously, if your function is a strictly convex function, then the stationary points x star, y star is a global minimizer, okay, on the feasible set. And moreover, it is unique because it's strictly convex, okay? So not only is x star, y star a local, strict local minimizer, okay? This is this is what we obtained when we got the second order sufficient conditions when we use the Hessian of the Lagrangian. But here, it's also a global minimizer, okay, that is strict. Okay, why? Because not strict, but unique. Okay, so why is that? Because we have a strictly convex function, strictly convex objective function. Therefore, the global minimizer is unique, according to the theorem that we had a while ago. So let's have another example, which is a utility maximization example. So suppose you have a consumer that has income B and has the following utility function. Okay, so consumption of goods X and Y enter into the utility function, okay, in such manner. So we have X raised to the 1/2 and Y raised to the 1/3. Okay, so X 1/2 times Y raised to 1/3. Okay, so so if you consume X and Y bundles, this will give you a certain satisfaction or utility, and that utility is given by this function. Okay, and those two goods X and Y have prices P1 and P2, which are given, okay, respectively. So the problem for this particular consumer is to maximize this utility, okay, X raised to the 1/2 times Y raised to the 1/3, subject to her budget constraints. So P1X1 is the consumer's expenditure on good X. P2Y is the expenditure of the consumer on good Y. Okay, so it's price times quantity. And the total expenditure should be equal to a certain budget. Okay, so you must not overspend. So now here we construct the Lagrangian. How do we construct the Lagrangian? So the Lagrangian is simply, again, f of xy, which is your objective function, plus lambda b minus g xy. Okay? So in this case, your f of xy, your objective function is x raised to the 1/2 times y raised to the 1/3. And then we have a plus lambda, and b here is your budget minus this is your expenditure, the function of the expenditure, which is a function of x and y. Okay, so your gxy in the previous slide was equal to p1x plus p2y. So negative g of xy is this one. Great, so that's Lagrangian. The first order necessary condition says that you take the gradient or the first order partial derivatives of this Lagrangian with respect to lambda, x, and y, and then you equate it to 0. Okay, so the first order partial derivative of the Lagrangian L with respect to lambda, lambda only appears here, so this is the this is the derivative, so b minus p1x minus p2y, then you equate it to 0. And then the Lagrangian with respect to x is the first order partial derivative of this Lagrangian function with respect to x. So you have x here and x here. So here we have 1/2 x, then you have 1/2 minus 1 in the exponent, so it's x negative 1/2. Treat y as constant, so y 1/3 raised to 1/3 is still there. And you have x over here, so this derivative is negative p1 times lambda is equal to negative lambda p1. Then you equate it to 0. And then finally, the derivative, first order partial derivative of the Lagrangian L with respect to y appears here. So bring down the exponent. This is 1/3. Treat x as a constant, so x raised to 1/2. And then the exponent of y is 1/3 minus 1. It's negative 2/3. So this is y raised to negative 2/3. And then lambda appears here. Y appears here. So that derivative is negative p2 times lambda, which is negative lambda. Then you equate it to 0. So those are the first order necessary conditions. Okay, so I've written the three first order conditions from the previous slide on the upper right hand portion of this slide. So notice if, okay, let's just number it 1, 2, 3. Notice that if we use 2, equation 2, it means that, okay, moving things around, we have that, oh, sorry about this one, we have that lambda, okay, moving lambda here, lambda p1, lambda is equal to 1/2 x raised to negative 1/2 y 1/3 divided by p1. Okay, so divide everything by p1. Great. So this is equal to lambda. Since we have an x negative 1/2 here, it's the same as putting this in the denominator. So you have 1/2 over here, and you have x raised to 1/2 over here, the denominator. And then you have p1 also in the denominator. Okay, and then you have y 1/3 left in the numerator. Okay, so this is equal to this expression over here. Great. Now using equation 3, we have that lambda is equal to 1/3 x 1/2 y negative 2/3 divided by p1, p2 rather. So in the same manner, you have that lambda is equal to 1/3. Okay, so y negative 2/3 is the same as putting y in the denominator and raising it by 2/3. Okay, and then you have a p2 here in the denominator. Finally, you have an x raised to 1/2 in the numerator. And this expression is equal to this one. Now notice that both these expressions are equal to the same number lambda. Okay, the same value lambda. So in essence, these two expressions are equal. Great. Okay, so next thing is that we cross multiply. So if we put this denominator, cross multiply this denominator here, and this denominator over here, we have that 3p2y 2/3 times this y 1/3, okay, is equal to 2p1 x 1/2 times this x 1/2. Okay. Now notice that this exponent added is equal to 1, so this is equal to 3p2y is equal to 2p1. Oops, 2p1. The exponents all sum to 1, okay, because they have the same base, so you can do x 1/2 plus 1/2, so it's x raised to 1. Okay, so this expression over here is this expression over here. Great. Now you saw y in terms of x, so we just put 3p2 in the denominator here. So y is equal to 2p1x divided by 3p2. Okay, so I hope everything's clear so far. Okay, so I've put our expression for y, which we have derived in the last slide, on this upper right corner. Now what you do is to substitute this y to the budget constraint. What's a budget constraint? It's just P1x plus P2y is equal to B. Okay, so let's substitute uh, this one to this budget constraint. So we have P1x plus P2 times y equals to B. Great. And so your y here is this one. Okay. So in this case, once you move things around, um, we have that P1x is equal to B minus, now the P2 cancels here. So we have B minus 2P1x uh, over 3. Okay, so let's just isolate P1x. So let's move it back. Sorry about that. So we have x over here. Let's isolate x. So you have P1, okay, P1 minus P1 minus 2. Okay, so you have P1 minus uh, in this case it's plus 2/3. Okay? 2/3 of P1. Okay? This is kind of convoluted, but bear with me. So in this case, x uh, we have 3 over here. We have 3P1 plus 2P1, okay, equals to B. And then we have x equals to x times 5P1 divided by 3 equals to B. So therefore, x is equal to 3B divided by 5B1. Okay, sorry for the convoluted way of solving this one, but this is how we got this expression over here. Okay, and so therefore, when inserting this x star into this equation for y, so y is equal to 2p1, your x is equal to 3b over 5p1, that's the x expression, x, and then we have to divide everything by 3p2. Okay, let's see if we can have things canceled. So we have here 3, this cancels. We have p1, this cancels. So therefore, we have, in the end, 2b. Okay? 2b is the only thing that's left here, divided by 5p2. Okay? So we have 5 here, we have p2 here in the denominator. So we have 2b divided by 5p2, which is exactly this one. Okay? So this is how you have obtained y star. So now we have x star, y star, which are our stationary points. Okay, this is equal to 3b over 5p1, uh, and then 2b over 5p2. Great. So from our previous slide, we have an expression for lambda. So lambda is equal to x raised to 1/2 divided by 3 times P2 y raised to 2/3. Okay, and so once you substitute x for this one, okay, x here, and then the y for this one, okay, you can do it yourself, but you'll end up with lambda star. Okay, so this is the expression for lambda star once you substitute x star in this x and y star for this y. Okay, so now it's couched in terms of B, and then the prices P1 and P2. Okay, now, so in order for us to determine whether the stationary points that we have obtained the previous slide, lambda star, x star, and y star, are local maximizers, we need to look at the Hessian of the Lagrangian function. Okay, so recall that the Hessian of the Lagrangian function lambda xy. In our case, it's just the matrix of second order partial derivatives. So in this case, it's L lambda lambda, L lambda x, L lambda y, L x lambda, L x lambda, L x x, L x y. This is L y lambda, L y x, and then L y y. Okay, so these are the second order partial derivatives in this matrix, the Hessian matrix of the Lagrangian. Okay, so again, you must know this by now. So for example, L lambda lambda is the derivative of this. This is L lambda with respect to lambda. Since lambda doesn't appear here, then we have 0. Okay, so L lambda x over here is the derivative of L lambda with respect to x. So x only appears here. So this is negative p1. With respect to y, L lambda y is a derivative of this with respect to y. So we have negative p2 over here. Okay, so that's how you get it, and then you go through the rest. Okay, and so we have an expression for the Hessian matrix over here. Now, you notice that these are functions of x, y. Okay, so in this case, you substitute h lambda star, x star, y star over here, and then you get the determinant. Okay, but uh, but just getting the determinant of this matrix, we have this expression over here. I don't want to get into the details of getting this determinant because it's bloody, but this just take it on faith that this is the determinant of H, this Hessian matrix over here. Now notice that in this case, we have expressions of x and y over here. Since you know that y and x are levels of consumptions, they couldn't be a negative uh, number, okay? And so therefore, you must have positive consumption of x or y. Then this determinant, since x and y cannot be negative, this is greater than 0. Well, the correct way to do this is to substitute the x and y with x star and y star. So you have x star and y star a while ago, which is x star, which is equal to, let's just go back, 3b over 5b1, and then y star. So x star over here is equal to 3b over 5p1, and then y star is equal to 2b over 5p2. Okay? So what you do is to substitute this one to this x's, okay? Okay, and then y to this y's, and you can very well tell that this is bloody, but the point is these are positive numbers, okay, because you have P1 and P2 are positive and B is positive, you have positive budget. So therefore, the determinant of H, let's just put it correctly, the determinant of H at H lambda star, X star, Y star is equal to a positive number. So therefore, we have that x star y star is a local maximizer of u, according to the theorem we had a while ago. So, great. Okay, so x star y star, that stationary point is a local maximizer. The question is it a global maximizer? And I leave that to you as an exercise, but as you well know, this involves getting the concavity or convexity of the objective function, and that's using the Hessian of that objective function. I leave that to you as an exercise.